Hola. ¿Se escucha? Sí. Bueno. Bueno, gracias por venir. Bueno, voy a hacer la formalidad en castellano. Es un gustazo tener a Thierry Giamarchi de visita, profesor invitado por el programa Maldacena. Bueno, Thierry está en el departamento de Quantum Matter Physics en Suiza, en Ginebra. Bueno, voy a leer la mini bio que estaba, ¿no?, como se acostumbra. Bueno, Thierry se graduó en la École Normale Supérieure de París y el doctorado lo hizo en París, en la Universidad París 6, en el 87. Fue miembro del CNRS, hizo postdoctorado en el laboratorio Bell. Después se fue a Ginebra, donde tiene su grupo, en el departamento de materia condensada de Ginebra. Y bueno, y es miembro de la Academia de Ciencias de Francia y de Estados Unidos. Bueno, su trabajo de investigación aborda efectos de interacción en sistemas cuánticos de baja dimensión, en particular, como líquidos Luttinger, efectos de desorden en sistemas clásicos y cuánticos, y bueno, en particular, bueno, tiene estudios que demuestran la existencia de nuevas fases desordenadas, como el Bose-Glass y el vidrio de Bragg. En el año 2000 recibió el premio Abraham de la Academia de Ciencias de Francia. Bueno, es autor de un montón de publicaciones, más de 200, tiene un libro, un muy lindo libro de Quantum Physics in One Dimension, que bueno, tiene mucho que ver con lo que hoy iba a contar. Y bueno, y muchas cosas más. So now I'll switch to English. Again, it's a pleasure to introduce Thierry. His visit is very inspiring. And well, there's some things I want to say. Well, Thierry has been lecturing in solid state theory, quantum theory of solids with Liliana. He has been giving some seminars, several seminars, and discussing with many colleagues. It was quite nice. But well, in addition, I would like to add something that is very special and important, which is not mentioned in his mini bio, is that Thierry is an accomplished magician. I mean, I won't be surprised if he has a deck of cards here and coins, and he's specialized in close-up magics. Well, so you can imagine that in every conference, I mean, he's performing twice, one as a lecturer, and then as a magician in lunch and dinner, so it's very nice, exciting in the audience. And he has a phrase that I like very much, which he says that a scientist or a physicist, the physicist's job is to explain the tricks that nature plays on us. So I like very much this phrase. And well, with this, I let Thierry explain all these nature tricks about the bizarre one-dimensional quantum physics. Okay, thank you, Thierry.
Thank you very much, Ali. So, thank you. I don't know if I should stand here or here. Let me try to go there for the moment. And first, I would like also to give a lot of thanks first to Ale for the very, very kind introduction. I must say it's a very great pleasure to visit Bariloche. I've had nearly now 1 month here, and it's extremely stimulating. It's fantastic to have all these interactions with the physics group in Bariloche. I must thank, of course, the group of theory of condensed matter. I must thank the Institute Balseiro and, of course, the Maldacena visiting program, thanks to which I could come here. It's always a great pleasure to be here. As I was telling at other seminars, I've known people in Bariloche for now more than 30 years. Carlos, Karen, Alberg, and others, of course. And my first contact with Bariloche was with H-bar different from zero, quantum mechanics and things like this. And then a little bit later, I realized that this place was not only a fantastic research institute in quantum physics, but it has something which satisfies also my schizophrenic career as a theorist, which is that it has also outstanding research in disordered classical systems. And my first coming to Bariloche actually in 2001 was for a conference organized by Paco de la Cruz on the pinning of vortices in type 2 superconductors, at which I had occasion to meet him, meet Daniel Dominguez, and some of his students, but we will come back to that at the next slides. So it's a real pleasure to be here. I had to choose something to tell you about, and as I said, I have a little bit this schizophrenic aspect, disordered systems or quantum systems. Finally, I opted for quantum systems, so I'm going to tell you about one of my love, I would say, which is one-dimensional physics. As was indicated, I am in the Department of Quantum Matter Physics at the University of Geneva. So for those who don't know Geneva, it's a city with a lake, mountains, and chocolate. And I'm sure you will notice the analogy with Bariloche. I have also the great honor to be the president of a network on materials with novel electronic properties. If you want to know more, I encourage you to go on the website, which is manep.ch, and discover more. So I will tell you about many things to which I'm not necessarily the main player, although I've played in this game for some time. So I cannot resist showing you my group at the University of Geneva in its current incarnation. So all these people are more or less working on low-dimensional systems, low-dimensional quantum systems. And of course, this is something that comes in my own career with many contacts and many interactions. You know, when you do science, you don't do science alone, but you benefit from interaction, discussion, sometimes fights with a lot of people. And the person who gave me the virus for this is my PhD advisor, the late Heinz Schulz, unfortunately, who passed away too young, and many, many others. And we had also the pleasure to collaborate with many, many experimental groups, both in the field of condensed matter and cold atoms. But there is one subset of people that I want particularly to acknowledge and thank on these slides, is that during my career, I had the great pleasure to interact, exchange with very talented, at the time, young people. No, sorry, it's a bad joke, it's a bad joke. Coming from Argentina, I'm sure you recognize some of them. Some are hiding in the audience, some were visiting last week, and I wanted to thank these people from the bottom of my heart for all the fantastic physics we could do together, and we are continuing to do together, and for all the stimulations and the interactions we had. And I had the pleasure to do some very short lectures, and I want to thank Liliana Rachea for that with the students. And from what I've seen, I can say that the torch is kept very high with the, with the new generation. So I'm very happy to say that I'm sure there will be future generations that will carry the torch at the level where these people carried it. So without further ado, let me tell you a story. I will not try to sell you a product or whatever, but I will tell you a story in fundamental physics. And before I go to one-dimensional systems, let me track back. I'm a theorist in condensed matter, and my goal is to understand materials. And as you know, materials have played a central role in humanities. They are all age of humanity which are named after a single material. You have the age of copper, you have the age of bronze, and so on and so forth. And we could ask, what is the age of the 20th century? I didn't say the 21st, I said the 20th. And material play a central role, and to tell you about it, let me show you this. Now, I'm sure the younger in the audience are wondering, what is this? Of course, people who are a little bit more my age, we recognize this. This is called a vacuum tube. And this is something where you emit electrons here. Then you have a grid that can repel or attract them, and you collect them on the other side. And this is something that is used to, was used to amplify current. And you recognize them, you get them. They are now in very fancy Wi-Fi amplifiers or whatever. And they were used a long time ago, 1947, to construct one of the first computer, which was called the ENIAC here. And read what a scientific journalist is reading about the ENIAC. It says, so this is a serious journal, it would be Scientific American or something like this nowadays. It says where a calculator of the ENIAC is equipped with 18,000 vacuum tubes and weighed 30 tons, the computer in the future may have only 1,000 tubes and weight only 1.5 tons. And you can see the scientific journalists going wild, you know, the fantastic extrapolation of everything. And clearly, we did much better. This was in 1949, and we did much better. And the reason why we did much better is because there were people doing fundamental physics, and these are these three people who got the Nobel Prize in 1956. It's Bardeen, Shockley, and Brattain, who invented the transistor. And they invented the transistor because they knew quantum mechanics. And using quantum mechanics, they could master materials enough to realize they could do much better than the vacuum tube to amplify. And this is something that has totally conditioned the society in which we live. By the way, for the students and for the little story, Bardeen is the only physicist who got 2 Nobel Prizes. Well-deserved, one for the transistor, one for the explanation of superconductivity. So this is someone who knew what he was doing. So essentially, if you had to qualify the 20th century, you would definitely say this is silicon. I think it's the French version. This is Silicon Age. This is something where essentially we have the information society in which we live. So how do you master materials? And if you want to master materials, you have to understand how electrons are going in solids, and that's a terrifying problem, because you get 10 to the 23 electrons in a little piece of solid. This is more than stars in the whole universe. So this is a complex problem. All these particles interact. All these particles obey quantum mechanics, so they are partly waves, partly particles, and whatever. And all these particles obey weird principle like the exclusion principle, saying they cannot be in the same quantum state, and whatever. So this is a nightmare, and nobody is able to deal with this nightmare. But what we understand are free particles, non-interacting particles. And that is already not bad. The problem is that in real systems, the interaction, which is the charge interaction, the Coulomb interaction, is huge. And it corresponds to energies which are huge, 10,000 Kelvin. So normally, there would not be a solid in which you can throw away the interaction. You have to worry about the interaction. And so it's not so obvious to deal with properties of realistic system. And the person who saved the day is a physicist named Lev Landau, who got the Nobel Prize for what he did, and did a lot of things in physics, but he did a fantastic theory where he showed that if you're not too worried about identifying the particles, but are more worried about the excitations, actually, the free theory works very well. And the only price you have to pay is essentially that you have to change some constant, like, for example, the mass of the particle. So the interactions are changing the mass of the particle, but that's a small price to pay. You say, instead of weighting this mass, they weight this mass, and then I use free electron theory. And this was a really instrumental theory that conditioned all the solid-state physics of the 20th century, because it meant you could think in terms of free electrons. And then you understand why some materials are insulators, where some materials are metals, why some materials are semiconductors, transistor. You understand why you can get superconductivity. You understand why, if you put a magnetic field, you can get a giant magnetoresistance, and so on and so forth. So you can do a lot of things with materials. You can do light-emitting diodes. You can do a CCD camera, which is transforming light into electricity. Essentially, your cell phone is a concentrate of quantum mechanics and Landau Fermi liquid theory, if I could say, if I wanted to caricature. But this is very important because it means that the society in which we live is conditioned by this mastering of materials. Now, of course, in the 21st century, people have become a little bit more ambitious. We have exhausted many of the possibilities that we had to use the free electron theory, and people want materials which have new properties, like, for example, something which can convert heat to electricity, something that can convert light to electricity, and so on and so forth. And of course, you could imagine, like in the past, that you could do this without worrying with interactions. But it sounds very far-fetched. And unless you want to mix everything with everything in the periodic table, well, the point is that you need to understand interactions. And we are fighting very hard to try to go beyond Landau Fermi liquid theory. We are trying very hard to put the interactions between the particles, and it's extremely complicated. One good example of that is one special class of superconductors, materials we can transport current without losses, which were discovered in essentially 86, 87. We know they exist because they are there, they are in the lab, they can be studied. Nobody understands why they work. And most people in the community would say that interactions are a crucial ingredient to understand how they work. There is no consensus, so I cannot tell you this is the case or this is not the case, but this is very likely that you have to understand interactions. And I want to emphasize this is a formidable problem. You will not write 10 to the 23 equations, much less solve them. You will also not easily put this type of problem on a computer. This would be a completely separate talks, but there is something in the quantum nature of fermions, of electrons, which makes it very badly conditioned to be simulated on a classical computer. And so when you try to do this, you have intrinsic instabilities, numerical instabilities. It's not impossible, but it's extremely difficult, and the computational time grows extremely fast with the size of the system. So this is a real challenge to be able to solve this, and people are trying to find cracks, new algorithms, quantum computers, blah, blah, to try to attack this, but this is today a strong challenge. And I want to emphasize this is a real frontier of knowledge, because very often this is big to very small here. People have a little bit the tendency to think that one frontier of knowledge is to go to the infinitely small, to know what is in the nucleus, in the quarks, in the whatever, and that's where the frontier of knowledge is, and this is indeed a frontier of knowledge, the infinitely small. Or you go to the infinitely large, what is in the galaxy, gravitation, and so on. And what are the basic laws which describe the infinitely large? This is indeed another frontier of knowledge. And what I want to emphasize is that there is another axis here. And this axis is the case where the laws for few bodies are well known. Electrons in a solid are described by an equation which is well known, which is known as the Schrödinger equation, or sometimes the Dirac equation. But because there are so many of them, the physics is new. Not only the problem is more complicated, but the physics is new. New phenomena occur. Superconductivity, magnetism. And this is really, it's not because you know how two electrons behave that you will understand how 10 to the 23 electrons behave. And that's extremely important to understand this. This is the axis of complexity. Some people like Giorgio Parisi, who got the Nobel Prize not too long ago, were working actively in this field. But this is the axis on which quantum, I would say, many-body physics, solid-state physics, is moving, and this is where our frontier of knowledge is located. So this is a general problem, and of course I will not talk about this problem in general, first because I don't know the solution, but among all these strongly correlated problems, all these systems, I will try to focus on the case where I'm looking at systems which are one-dimensional. And now you could say, why? Why is one-dimensional special? Why would someone be excited about one dimension? And let me try to justify it a little bit by hand before we try to go. It's because, in a way, it's the dimension where the interactions have the most dramatic effect. And it's very easy to understand. Here in this room, you are interacting by an infinite repulsion. None of you can sit at exactly the same place than someone else. Nevertheless, you more or less behave as a free particle, because you could stand up and move and leave the room without interacting with your neighbors. You live in 2 dimensions here because you're not using the 3rd direction to float to the ceiling. So although the interaction is very large, it doesn't do much, and you can still think in terms of free particles. And that's what happens very often in 2 and 3 dimensions. Now imagine you're queuing for cafeteria, for movies, for anything. And you have an interaction with the person who is in front of you. You will move, you will push the person in front, we will push the person in front, we'll push the person in front, and so on and so forth. So immediately, your individual motion will become a collective motion. And the whole line has to move. It's the same thing if you're stuck in traffic with a big weekend coming on, beware. So here you see if there is only one lane here, this car is not behaving as an individual particle, but it has to go with the flow. It has to behave collectively with the other. So even a relatively weak interaction in 1D is having totally dramatic effects. And so that's the dimension in which we can expect the most fun out of the interactions. So I like it. For the more specialist of the subject, we are usually, when we solve a problem, we assume that there is a certain degree of order. And then we do small perturbation around this order. Well, in 1D, that's the worst dimension to do this, because there are so much fluctuations. The system is vibrating, if you want, around the order that you cannot do this. So not only the physics is different, but even the technology, the methods that you're using, you cannot use the same methods than the one you use in higher dimension. So this makes it fun. And again, you know, beauty is in the eyes of the beholder. You like it, you don't like it, but it's certainly a fun place to look for the interaction effects. So there are 3 urban legends about 1D that I would like to blast during this colloquium. The first one is that 1 dimension is a kind of toy model. You know, this is something which is a simplification of higher dimensional systems. As I said, the physics is very different. The second is that it doesn't exist in nature. It's something which is just an invention of theorists to occupy their long winter nights, and this is sad and all this. Okay, it's not true. I will show you a lot of experimental examples. And the worst urban legend is that everything is understood there anyway. You know, if someone tells you there is this field and we understand everything, do something else. This is not a field for research, but I will try to convince you that there are very deep questions that people need to address in this field. Of course, I will not do any calculation or whatever, so I will not be more explicit in step 2. That will be just what I will give you results, but that's it. I have put here, it will appear on the video, a couple of references for the more specialized people or the one that would like to know more. There is a very recent review that has been written with many hands, each person being a specialist of one experimental system or a theoretical method to sort of do the state of the art on 1D. It's not the most easy to read, but if you want to have reference or things, you can look at it. Okay, and now we'll explore. I'm doing fundamental physics. Of course, as I told you, there is an interest behind, which could be to do device, which could be to do electronics, which could be to do things which are useful, but I will not talk at all about this. I will play a symphony for you. I will play music. I will do something which I find beautiful, and I hope you will find beautiful, but I will not try to justify that it's useful for society or whatever. I don't care. I just would like to understand. And let's explore. So let me tell you about a fun property of 1D physics, which I will try to explain. And I will try to explain with little cartoons. Imagine that in a solid you have little magnetic moments, which people call spins, And this little magnetic moment points in certain directions. And we are trying to understand what are the excitations on the top of the state, which is like you are in what is called the ground state. You are calm and whatever. But then one of you can jump on the chair and you get an excitation. Here, the excitation will be this. I turn one moment. And the minimum excitation you can do is to turn a moment from up to down. So if S is the size of the moment, the excitation will be of size 2S. You flipped it. Let's say +1 to -1, 2. Okay. And that's the minimum you can do. And in 3D, this is exactly what happened. This excitation has a name. It's called a magnon. It's a magnetic excitation that can propagate in a solid. And this excitation is like a particle. It's like these 3 spins which are down together. And if I give it a momentum, if I give it a kick, it will have an energy which is only a function of its momentum. So I have an excitation, and I cannot do less than this because the thing I can do is turn more spins, but I can turn less than 1 spin. Now, let's do the same thing in 1D. I know this is also 1D, but it's because I didn't want to put more things. So let's do this thing in 1D. So I turn a spin. And if I turn a spin here, now I can let the other spin evolve using the laws of quantum mechanics, so trust me on this. So I'll do it. So these 2 spin evolve, these 2 spin evolve, and so on. And now we go a little bit faster on the other side. And then you see it's very weird because my 3 spins which were close by are not there anymore. But I have 2 places where I get 2 spins which are close by. So it's a little bit like if my magnon has melted into 2 new excitations. It's like if my particle has disintegrated into something which is not really a particle because it's not local. It's something where there is a whole part of the material which has been turned the other way. And then these objects, if you look at what they are, they carry an excitation which is only half of the previous one. It's logical. You take 1 particle, you break it into 2, you would say. But this is impossible. It's like if I was telling you, I take 1 electron and I cut it in 2. I get 1/2 of an electron and 1/2 of an electron. You would tell me, no, it's impossible. It's an elementary particle. You cannot cut it. Well, that's exactly what happens. And that's part of the bizarre physics that can exist in 1D. And the reason why it can exist is because these objects here are actually not local objects, but they carry very far, and then you get the second one. So this non-locality, this non-really local object here, allows fantastic things. It allows to fractionalize the elementary excitations. In higher dimension, you cannot do less than 1 electron. Well, in 1D, you can. You can have an excitation which will carry a fractional charge. And that's something which is remarkable because we are not used to it. So this is one example. It has, people gave it a beautiful name. It's called spin-ons. Well, it's spin and when you want to do a particle in physics, you put on at the end. So magnon, spin-on, whatever. Okay, you will see other examples. So here is my spin-on. It's like my magnets, and then suddenly I turn everybody on the right, ploop, by pi, and that's exactly my excitation. So it has a lot of features that I will not insist on. It has something which people call a topological order. It has a continuum of excitation because, of course, I can break my original particle in 2. So I can distribute the momentum as I want among these 2, and then the energy of the particle will be the sum of the 2 energies, which means instead of having a good relation between the velocity, let's say, the momentum of the particle and its energy, I now can do a lot of choice. I can take this as I want, and this will give me plenty of possibility to excite my system. So this is something very different than what we expect in a higher dimension. Let me do it for you with an electron. I was mentioning the electron. You could have told me the electron is more fun because it has charge and it has a little magnetic moment, which people call the spin. So what can I do? I have my 1D system. I can remove one electron. If I remove one electron, I remove a charge and I remove a spin. And that's the best I can do. I cannot remove less than a charge and a spin because this is the electrons. Now, let's the system evolve, and you will have, again, the spins are moving, blah, blah, blah. And you see here, I have no charge missing here. But I have two spins which are pointing down. So I have an excitation which carry only the spin, but no charge. And here, if I let the charge move, I will have a place in the system where I will have an excitation, which people call holon, okay? This one is the spin-on, you know. And this place here, there is an excitation where there is a charge missing, but the spin is up, down, up, down, up, down, so there is no spin missing. And so it's weird, your electron has melted into an excitation that has only the charge and an excitation that has only the magnetic moment. You can imagine that, for example, the conductivity, the transport properties will be very different than what you would get in higher dimension, because in higher dimension, both the charge and the little magnetic moments will have to move together. So these are two examples, or one example, if you want, this fractionalization of weird properties that 1D systems have. So I won't insist on this, just to tell you that you hear the name at least once, that there is a kind of universal type of properties like this that exist in 1D, and these properties go by the name of Tomonaga-Luttinger liquid physics. The gentleman who coined the name is this gentleman here, whose name is Duncan Haldane, who got the Nobel Prize for other works than this, but who did also a pretty damn good work here. And so we are in a fantastic situation here because we know that there is this set of very weird properties which are a little bit like the Fermi liquid theory in 3D. So we have in 1D or Fermi liquid theory if you want, except it's weird. And therefore we can use these properties to try to understand the system which are interacting in one dimension. Now, let me show you, because I told you, oh, it's fun, it's nice, it's weird. You could say, yeah, but does it exist? And so let me show you. Here in condensed matter, for example, here is a compound which is made of molecules which are a little bit like plates you can stack, and the electrons can move very easily in this direction, but it's very hard for the electrons to jump from one stack of plates to the next plate. So in a way, the material is three-dimensional, but the motion of the particle is mostly one-dimensional. So this is a set of organic materials which was synthesized by this gentleman whose name is Klaus Bechgaard, and it bears his name. They are called the Bechgaard salt, and I pronounce it very badly. The first time I heard it pronounced by people from the Nordic country, I didn't even recognize the name. So this is something like Beckgord or something like this, anyway. And what people found is that these materials are very weird. And in particular, my colleague Denis Jérôme at Paris-Saclay found that there is superconductivity, so these materials can transport current without any dissipation. Why? Nobody knows. But there are very good realization of one-dimensional systems. So one-dimensional systems exist, at least within a certain range of parameters, and they have, in addition, very weird properties. If you want to check it, you, for example, measure the frequency-dependent conductivity of these materials, and trust me on this, you should find some power law, some very specific behavior, and this was done by these gentlemen, Martin Dressel, George Gruner, and Leo De Giorgi, using a technique that I don't want to discuss. And lo and behold, you see that if you plot the frequency-dependent conductivity of these materials, you find a very nice power law over more than 1 decade, which confirms pretty well that these materials behave the way they should behave. And this was, I think, the first observation of this type of behavior. Now, the fractionalization, you could say it's weird. Does one see it? Yes, one sees it. For example, the fact that you have this continuum of excitation that I was mentioning, it can be seen by neutron diffraction experiment. I will not tell you what neutron diffraction experiment here is. There is a neutron reactor not very far. I think it's probably used to do some neutron diffraction. It doesn't matter. You're measuring the correlations between the little moments as a function of the momentum of the excitation and its energy, and the color code is the intensity. It doesn't matter. Remember this little drawing that I was doing before. This is where you expect to be able to get excitations. And lo and behold, when you do the experiment, which was done by Christian Ruegg, my colleague at the Paul Scherrer Institute in Switzerland, you find something, and when you compare with a theoretical calculation, which was done by Jean-Sébastien Coe at the University of Amsterdam, you find an excellent agreement. So this is an indirect proof of the fractionalization. Can one see a more direct proof? And the gentleman who attempted to, and did, see it is Amir Yacobi here. At the time he was in Weizmann in Israel, now he's in Harvard in Boston. And the idea is to say, let me take two one-dimensional systems, which are what are known as quantum wires. These are extremely narrow semiconducting structure, which are so narrow that everything is quantized in the perpendicular direction, and only the motion in this direction is possible. And then let me try to make the electron tunnel from one of the wire to the next. And he's putting a magnetic field and a gate voltage to do unspeakable things to the poor electrons. But the idea is that if there is no fractionalization, I will see tunneling and I will see only one mode, one curve. But if the electron is broken into two, it has to reconstruct before it can jump, and therefore I should see two modes. Now you can discuss here whether you see one mode or you see two modes. The least one can say is that it's not totally obvious, but they were smarter and they say if there are two modes, then you can get, interference. Like when you have two sounds which are very close to each other, you hear the sound which corresponds to the modulation. And lo and behold, they did the experiment. The theory was done by Bert Alprin and Jaroslav Cherkovniak, and they got something which was a reasonably good agreement with the experiment. So this is one experiment that is trying, and did, I think, show spin and charge separation. And many others. I will not go to details. Now you could say, okay, it's very nice, but everything you showed us, the dates were 1998, whatever. So anything new in the 21st century? And yes, there are a lot of things which happened. First, we have new methods, fantastically new methods. I will maybe come back to it. I will not spend too much time. We have new systems, and I think it's the most important things that they are, in particular, cold atomic gases, which have provided fantastic realizations. And more importantly, people have worried about new questions. So I will just show you the new experimental systems, because I think it's very interesting to see this. what people realized recently is that you could trap and cool atoms by lasers. And this is a long-standing series of research which brought several Nobel Prizes. And of course, the idea is that if you trap something in a prison without walls, the walls cannot warm the object, so you can cool it even better. So here is an example of fluorescence of a little, I think it's sodium, blob that was trapped by lasers. And because you have no walls, you can cool this little blob extremely low. And when I say extremely low, we are talking about 10 nanokelvin. So this is much colder than the cold of the vacuum of the universe, which is around 2 Kelvin, 0 Kelvin being minus 273 Celsius, just to give you the scale. So when we are at 10 billionth Kelvin, this is really, really, really cold. Okay. Well, now you would say, why would one do something like this? So in practice, it looks like this. This is an image of my colleague Tilman Esslinger in Zurich. A lot of lenses and lasers. The idea is, if I can trap atoms in traps of light, I can make a periodic light potential. And then my atoms will jump from one side here to here to here. This is light. The red ball is an atom, a little bit like you here, except the chairs would be made of lights, if you want. Now, this is exactly like a solid. A solid, you have the electrons which are moving in the periodic potential due to the ions, due to the nucleus of the particles. But there, you could have the atoms who play the role of the electrons, and the periodic potential would be made of light. You would have the atoms which are filling each other when they are in the same well, and so on. So you can do artificial solids. And this is a proposal that was done by essentially the group of Peter Zoller. And this was something which started a whole industry because people realized they could do artificial solids and do a certain number of experiments on these artificial solids. So, for example, here we will not go into detail of the experiment, but is an experiment done in the group of Randy Hewlett in Texas, where he was realizing with this artificial solid a 1D interacting gas of fermions, so like a gas of electrons, and then measuring their excitations, and you can compare with Thierry, and you find excellent agreement between the observation and the theoretical calculations, which made some journals say ultra-cold atom confirm 50-year-old physics theory. I don't know if it was meant as a compliment or as an insult, but okay, that's fun. Spin charge separation. I told you, you see with the tunneling, you see some indirect view of the spin charge separation. Here is experiments done in the group of Immanuel Bloch in Munich. They don't see indirect. They take a photo of the particles. So here is not a simulation or it's not a drawing, it's the result of the experiment. What is on the top are the atoms with a little spin up. What is on the bottom are the atoms with a little spin down. When there is nothing, it means there is nothing. When there is something here, it means something up. When it's something here, it means something down. And then you can take a photo, you see here, and you can check that indeed the structure that is here is exactly the one I showed you in my little cartoon. So you can directly study the dynamics of this particle, and therefore you can directly test for the spin charge separation. So this is really absolutely gorgeous experiment where people check that indeed when you get the hole on, when you get the hole, it's surrounded by down, up, and so on, and you can study this kind of things much more in details. Of course, I will not go here. Randy Hewlett did also things where he was able to test the spin charge separation. So these new systems were really bringing direct measurements of this weird physics, which is a little bit more difficult to test in condensed matter. People got new theories, not new methods. And more importantly, they managed to combine methods. Why? Because when we try to solve a problem, usually there are two ways you do it. Either you're someone like me who has been trained to do calculation with pen and paper, and you try to do what people call field theory or many-body physics, and you usually have something which works when you look at the system at large distance, low energy, long time. That's good. There you can say a certain number of things. And then you have people who do numerics, and numerics is fantastic because if you have the microscopic model, you can usually solve pretty exactly. But numerics has also a limitation. Size is finite. Time is finite because computational time is finite. So you're usually good at short time, short distance. And how short is, of course, all the crux of the matter. But generally, I would say people doing analytics, they are happy at large time, large distance. And people doing numerics, they are efficient at short time, short distance. And very often, it's two worlds. In 1D, and I won't go in details how, people manage to bring the two methods together. So what you can do, you can either use the numerics to directly obtain the solution, but if you don't know how to do this, you can inject in the analytics things that you take from the numerics that give you the possibility to have your analytics exact. So I don't want to go too much into details, but there is a take-home message that we know how to get the best of both worlds and combine the methods. I will just show you an example on a very weird compound, which is this one, which has little magnetic moments here. And people study this by a technique which is called nuclear magnetic relaxation. And it's very hard to compute the relaxation time in this material. So this is, you see, a material which is a little bit, again, made of 1D structures here, which are well decoupled in the material. So the material is 3D, but you can consider that its physics is 1D. And then people try to measure a certain number of quantities. And if I'm doing an analytic calculation, this was done in the group of Claude Berthier by Martin Klanczek, and Pierre Bouillot and Corinna Collat did the theory. Voilà. If I do an analytic calculation, I will give you this formula. It doesn't matter what this thing is. I give you this formula. Except in this formula, I don't know what U is. I don't know what K is. I don't know what A is. I don't know their numerical value. I don't know these numbers. So I can tell you, look, it should vary as a power law. Fine, then I would fit and see it's a power law and whatever. Now I can take numerics, and from the numerics, I can tell what U is, what K is, what A is. So this formula becomes essentially exact, no adjustable parameter. And lo and behold, here it is. This is the comparison between the experimental data, and the red line is the formula. No adjustable parameter. I never thought in my life that I could see that in solid-state physics. It works. Now, I could stop here, but if I stop here, I would not blast the last urban legend of 1D, which is, I told you everything works. So is it the end of the story? We have quantitative agreement, everything works. No, of course, because now we are in the same situation with 1D systems with Tomonaga-Oettinger liquid than people were in the 60s with Fermi liquid theory. Now we can have fun. We can couple 1D structure, we can extend them, we can stack them, and go to more complicated problem, and we have a good building brick, which is this Tomonaga-Oettinger liquid theory, to try to go beyond. The same way that people went beyond with Fermi liquid theory. They discovered superconductivity, they discovered giant magnetoresistance, they used it to understand a lot of materials. So here is the same. I will, of course, not do to you general statement of everything that can be done, simply because I don't know what can be done. We need you. Go and have fun. Couple 1D systems, but I will show you one or two examples. Okay, one can do perturbation. You add a lattice, you add disorder, you mix systems with different components. You try to study new type of phase transition. For example, there has been recently a lot of activity on the topological phase transition, which was the Nobel Prize of 2016, and here is Duncan Haldane again, who played a major role in this field. You can study out of equilibrium situation. We are very good to describe thermodynamic equilibrium. Now, kick the system. We don't know what to do, but we have the basic theory, so we can at least build on this to try to go beyond. Let me just show you a beautiful experiment done in the group of Tillman Esslinger. Here is a fantastic transport in 1D. One big blob of atoms, another big blob of atoms. They can pass a current here. And then with light, with the equivalent of the projector, of the beamer, a DMD, something which you can program the shape you want lit or not lit. They can imprint whatever structure they want on the channel. Here, they put something periodic. So this is, again, creating a 1D solid, and then they can push the atoms here and study the transport. And, of course, the question is, what is the theory that we need to do? We can try to start from this Tomonaga-Luttinger liquid and try to go beyond. We can worry about the dimensional crossover. Now we understand very well the 1D system, but as I showed you, many systems are not made of a single 1D chain, but many one, which are coupled. Let's try to go back to the spin charge separation if I have more than 1D chain. Here. Remember, one single chain, I told you spin and charge separate. Let's try to do it. I remove one particle. And then I do exactly what I was doing before, but this time with the other chains. And now you see what happens. This is okay, and I get my spin on here. But you see, all these three, they are very unhappy because this chain has turned the wrong way. So now it will cost me an energy which is growing as this particle goes away, and same thing on the other side. So if I have more than one chain, the hold-on and the spin-on, they cannot go far, far, far. They are bound by a spring, and this spring will keep them together. And you know, you could say now I have the charge and the spin which are bound, and this is an electron. So the deconfinement, this fractionalization that exists in 1D, is prevented by the presence of the other chain. How this affects the property of materials, this is something which is really an interesting question. You can observe it in some materials. Here is an example of materials where you do neutron diffraction experiments and you see a set of resonance here in the neutron diffraction experiment. And this is a slice of what you see. You see this resonance. And what are these resonances? Well, if you have studied quantum mechanics, you studied the hydrogen atom. The hydrogen atom is a proton kept by a spring, okay, not a spring, but something akin to a spring, to the electron. And this produces the energy level. Well, here it's the same. You get two particles with a potential which keep them. They have resonances, and you can study them. So essentially, you get this type of phenomena. And again, to close the loop, that will be my last slides, if you look at real materials, even those which are made of chains, these materials have some degree of coupling between the 1D structure. So how do you go from the 1D physics, this very weird 1D physics, to something where the coupling between the chains, the hopping between the chains is now important? Well, this is an open question. And on that, we don't have the answer because the 1D technique failed, the numerics fail, everything fails. So one needs to invent new methods, new ideas, and possibly new experiments. Here, again, this superconducting phase, nobody has an idea. What is the mechanism? And even what is the symmetry, by the way. And this is clear. It's a phase which is made of weakly coupled 1D chains. Voilà. I stop here this tour that I made with you. Again, this is just intended as a little exploratory tour of 1D physics, which has very remarkable feature. And again, take it as one example of the effect of interactions in many body systems. This is much more general, of course. 2D and 3D are also very exciting, but 1D is really remarkable. So there is a theory which is called the Tomonaga-Luttinger liquid theory, which provides a very good framework to study this physics and, more importantly, to go beyond. And there are fantastic, challenging questions which are to be addressed today. This requires a lot of interplay of different techniques, so I think it's very exciting to be at this, in this field and to make progress in this understanding. And of course, what is the most important is that it exists in nature. There are many experimental realizations. So on this, I'll stop on the tour, and I'll let you with this word to explore, which goes from the fundamental physics to potentially applications. Thank you for your attention.
Okay, thank you very much, Thierry. Are there questions?
Yes. Thanks for a very nice talk.
Thank you.
And regarding this mention you made of the different methods, what do you think about machine learning? What could it, I don't know, help to understand in this area?
So that's a very good question. So for example, one of the methods which is intensively used is something called Giamarchi, density matrix renormalization group, which was invented by Steve White, and which is a variational method where you kind of propose a shape of the wave function and then you adjust to. People have tried to use machine learning to also propose variational wave functions. There is a very beautiful paper by Carleo and Matthias Treuer. So this is certainly one direction in which people could benefit from machine learning. But I would say this is to discover. This is a field which is really in infancy. Now, of course, for looking at the experiments or analyzing the numerics, people have also used machine learning to decide whether the result was telling them the system is insulating or not. So this is another direction. But I think even at the level of describing the quantum system, machine learning can be useful. But today, I cannot give you an example where it has cracked a problem.
¿Alguna otra pregunta? Well, what about quantum simulation and quantum computing?
Okay. So actually, the cold atoms are often called quantum simulations because they are realization of idealized models. For example, contrarily to what happens in condensed matter, the atoms here are neutral. So theorists, they very often take models where we consider that the particles only see each other if they are on the same site, and they don't see each other if they are not on the same site. This is, of course, a caricature of reality, and for the electrons in a solid, it's not true. There is the Coulomb interaction. It's not too bad because this interaction is screened, and at the end, it's not too bad. But here, it's not too bad, it's exact. The atoms are neutral, so the only residual interaction is very weak van der Waals forces here. So you have really a perfect realization of models that theorists are trying to solve, where you only have a repulsion if you're on the same side, and 0 if you're not on the same side. You have also the possibility to control at will, because this is a laser, so you control the amplitude of the laser, the tunneling from one side to the next. So very often, these things have been called quantum simulators, because in a way, by turning knobs in the lab, you can realize the equivalent of a model that theorists like to study. And then, by reading the experimental answer, you get the answer just like if you had done a numerical calculation, except it's a real experiment. So that's one thing. The other thing is that people are trying to use similar technology to do what is known as quantum computing. And there, it's trying to get a digital computer, same way than this one, I would say, but using quantum physics as an influx. This is still a direction which is, let's say, which needs to be further explored, but there are various powerful players, in particular the big tech company, that are trying to develop these quantum computers. Yeah. So all these are tools that we think would be useful for understanding correlated systems, because really this is a difficult problem.
Following the line of Cecilia's question, what do you think about application of density functional theory to these one-dimensional systems?
Okay, that's a very good question. So of course, density functional theory, which is a theory which has been introduced now a long time ago, in particular by Walter Kohn, and for which he got the Nobel Prize, is a theory which allows to describe realistic solids and to do really not only solids, also molecules, and this is an extremely powerful theory. And people have tried to extend this type of theories to be able to incorporate more strong correlation effect, and there are various techniques that people have developed. I won't enter in all details. I'll just mention one, which is called the DMFT, which is dynamical mean field theory, which is due in particular to Gaby Kotliar and Antoine Georges. And they try to combine this with the density functional theory. So it works very well in higher dimension. The lower you go in dimension, the more the fluctuations are killing you, and there are definitely effects that exist in one dimension that you will never capture with the density functional theory. So I think it depends what you want to capture. If it's a complicated molecule like this one, and you want to reduce it to a simple, I would say, model, then the density functional theory can really help you. And there are people like, for example, Henrik Canadell, who used DFT to describe these stacks of molecules and give you an effective model by which you can represent it. But then to solve this effective model, you need to go beyond DFT. So I think here again, the best is to combine the DFT, which will give you the simplified model, with then a solution of this simplified model, which will properly take into account the correlations. So for any solid state physics, DFT is a must, I would say, or DFT-like problems is a must. But in 1D, you cannot, unfortunately, stop at DFT because you will miss many of the correlation effects. So this is things which make it fun. The cold atoms, of course, they don't have the problem of the DFT part because usually their microscopic model is much more simple and doesn't have to deal with screen Coulomb interaction, high energy, and whatever. So there you really have to focus on the second part.
Okay, we thank Thierry.
Thank you. Thank you very much.